Hi class, we are now on 7.3a. There's going to be broken up into 3 different sections. So the first one, this is not too many slides. We're just going to introduce some more about the mole and balanced equations. So in the last lesson, we discussed the concept of the mole. In this lesson, we're going to see how we can use that mole concept with balanced equations to describe reactions at a scale we can measure in the laboratory or factory. So let's begin with the familiar reaction, which is water, the explosive reaction of hydrogen and oxygen gases to form water. We can read this equation in one of 2 ways. First, we can interpret it as a ratio of molecules. That is, 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. But we can also interpret this equation as a ratio of moles. 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. Okay, this is a very busy slide. I tried to clean it up some, but there's just really no way for me to, we're just going to have to deal with it. Because a balanced equation relates to the moles of a substance in a reaction, we can use it to connect the amount of one reactant or product to the amounts of every other species in that equation. So let's look at this example. So consider this reaction. We're going to look at 4 different questions that relate to this equation, and then we're going to answer them. So question 1 is how many moles of iron react? So to answer this, we need to convert from grams of iron to moles of iron. The molar mass of iron is 55.85 grams per mole, and we begin with 235 grams of iron. We then multiply that, so we're looking here, we multiply that by 1 mole of iron per 55.85 grams of iron. This gives us 4.21 moles of iron. Okay, and now in the second one is how many moles of HCl are needed to react with the iron. So we are looking at this one here. Based on the balanced equation, and this is a balanced equation that's right here, 2 moles of HCl are required for every 1 mole of iron. So what this means is 2 moles of HCl is required for every 1 mole of iron. Since we have 4.21 moles of iron, this means we need twice as many moles of HCl, or 8.42 moles. We can solve this problem using unit conversions. So we begin with 4.21 moles of iron. We multiply the conversion by HCl on top, which is 2 moles of HCl over 1 mole of iron on the bottom. This will cancel these out, and this gives us 8.42 moles of HCl. So them saying that we need to double this, I really don't do that. I actually work almost every single problem out. Just that's always how I've done. I see what they're trying to say here, but it can be confusing as some of these reactions get bigger and bigger. So I always just do this. Question 3, how many moles of iron 2 chloride form in this reaction? So now we're looking at the product side. In the balanced equation, there is 1 mole of iron, excuse me, let me take a look here. There's 1 mole of iron 2 chloride. I lost my place again. Hold on. Per 1 mole of iron. So 1 mole of iron 2 chloride per 1 mole of iron. Therefore, the moles of iron 2 chloride produced are the same as the moles of iron. So what it's saying is that if there's 4.21 moles here, there has to be 4.21 moles here. Again, I don't just do this. I actually work every problem out. So that's what we're going to look at, and they call this formally. So this is kind of informally trying to figure it out and actually working it out. They're calling this formally, working it out or writing a conversion factor. So here we have 4.21 moles of iron times 1 mole of iron 2 chloride over 1 mole of iron, and it gives us the same answer. I work it out always. I never just look at the equations and do that. So our answer is 4.21 mole iron 2 chloride. I'm sure some of you guys are really good at math and you can see that instantly. Even though, yes, I have chemistry degrees and work on this, I don't do those shortcuts. I just don't. I'm not comfortable with them. Question 4, how many grams of iron 2 chloride form? In this question, we have to convert from moles to grams. Anytime we convert between grams and moles, we use molar mass. Based on the masses of the periodic table, the molar mass of iron 2 chloride is 126.75 grams per mole. We know that we form 4.21 moles of iron 2 chloride. We use the molar mass as a conversion factor, which you can see at the bottom corner, and multiply by 126.75 grams over 1 mole of iron 2 chloride. The moles of iron 2 chloride cancel. This gives us a final answer of 534 grams of iron 2 chloride. Okay, so going on. This type of problem that we just did is called a stoichiometry problem. So it's a nice fun word right here. This is what is going to follow us through chemistry, never getting away from it. These problems use the amount of one material to predict the amount of another material that is consumed or produced according to a balanced equation. Once we found the moles of iron, which is problem 1, we were able to relate this value to both the moles of HCl and the moles and grams of iron 2 chloride. Given the amount of grams or moles of one substance in the balanced equation, it is possible to find the moles and grams of any other substance in the equation. So let's take a look at another problem. When magnesium burns, it combines with oxygen to form magnesium oxide. If this reaction consumes 3.0 moles of oxygen, how many moles of magnesium oxide will form? How many grams of magnesium oxide will form? There are two ways to approach the first part of this problem. The first part is by visual inspection from the balanced equation. So again, we're looking up here, this is the way I never do things, but it's in your book, or at least it's on the slides. We see that 1 mole of oxygen, so here we go, 1 mole of oxygen produces 2 moles of magnesium oxide. Excuse me, based on this ratio, 3 moles of oxygen gas will produce 2 moles of magnesium oxide. And I get what they're saying, but I have always worked out problems, so I don't do the shortcuts, which I've already stated. For simple ratios, this sort of visual inspection is very helpful. However, we can also solve by using the balanced equation to create a conversion factor. We begin with 3 moles of oxygen gas, then multiply by a conversion factor. Based on the balanced equation, we write 2 moles of magnesium over 1 mole of oxygen. The moles of oxygen cancel, giving us the answer of 6 moles of magnesium oxide. Once we have found the moles of magnesium oxide, we can convert from moles to grams. To do this, we use the molar mass of magnesium oxide. So you see the molar mass right there is 40.30 grams per mole. We begin with 6 moles of magnesium oxide, then multiply it by the conversion factor of 40.30 grams of magnesium oxide over 1 mole of magnesium oxide. So it's right here. The moles of magnesium oxide cancel. Rounding to 2 significant digits, this gives us an answer of 240 grams of magnesium oxide. We're going to do a lot of problems, so if this seems a little overwhelming, I'm going to have problems to show how to do this. Okay, so we're going to take a look at this problem now. So sodium metal reacts violently with water. How many moles of hydrogen gas form if 11.0 grams of sodium react with water? To solve this problem, we first must convert the grams of sodium to moles of sodium, then relate the moles of sodium to the moles of hydrogen. So we need to do some conversions before we can even look at the problem itself. To convert grams of sodium to moles of sodium, we use the molar mass of sodium, which is 22.99 grams per mole. We begin with 11 grams of sodium, then multiply by 1 mole of sodium. So we're looking at this top one right here. 1 mole of sodium over 22.99 grams of sodium. The grams of sodium cancel, giving us 0.478 moles of sodium. Next, we relate the four, so we take this answer, and now we're going to go from moles of sodium to moles of hydrogen. So next we relate the 0.478 moles of sodium to moles of hydrogen. Using the coefficients from the balanced equation, we write 1 mole of hydrogen over 2 moles of sodium. The moles of sodium cancel, giving us a final answer of 0.239 moles of hydrogen. For simplicity, we write these two steps into a single line. We begin with 11 grams, so it's the bottom one here, then multiply by the first conversion factor to change from grams of sodium to moles of sodium. We then multiply by the second conversion factor to go from moles of sodium to moles of hydrogen. Again, this gives us an answer of 0.239 moles of hydrogen. So I'm going to tell you that when we first learn this, it makes sense to break it down in two steps so you can understand what's going on. But as we go on, we don't do this. We don't do it in two steps. We do it all in one gigantic step. And sometimes these conversions can go a lot longer with more steps in between. Why? Because students, I feel like, and including myself, when you have to break it down in one step and another step, students make a lot more mistakes than just keeping like a long train of an equation. Sometimes they round when they shouldn't round because they're not done with the problem. They confuse sig figs. When you do something all in one step, you can kind of keep track of where everything is and see what cancels and what's remaining. And you don't always can do that when it break it down into steps. It can be more confusing. You may not understand that right now, but as we do this, hopefully it'll make more sense why we keep it streamlined into one equation or calculation. Summary of stoichiometric problems. Using a balanced equation, we can relate the amount of any one substance to the amounts of any other substance produced or consumed. This type of calculation is called a stoichiometry problem. When working with stoichiometry problems, there are two common conversions that we make. For any substance, we can convert grams to moles using molar mass. And when relating moles of different substances, we use the balanced equation to create conversion factors.